everyone. So in this lesson we're going to focus on some important concepts called displacement and velocity when it comes to physics, particularly when it comes to kinematics. Right? So I'm using this word kinematic or kinematics, and what does that mean? Right? So when it comes to physics, it's really important to be able to describe motion, right? And this is the whole purpose of this branch of physics called kinematics. It's describing motion. Now, objects can move in three spatial dimensions, right? They can move forward, back, side to side, and up, down, we'll go with. But we're going to first talk about linear motion, right? Also known as one-dimensional motion. So the motion of an object is restricted to a straight path, right? So it can still move back and forth along a straight line, but this will be kind of the simplest approach to learning kinematics. All right? So basically, if we're to kind of be able to track our object, we'll be able to kind of take, our ruler and line it up, and our object will always stay on that ruler type of thing. So what you should be able to do by the end of this lesson, right, you should be able to define the linear motion of a system and when and how it can be simplified to an object model. You should be able to define and explain relationships among distance, displacement, instantaneous velocity, average velocity, constant velocity, and speed. So, a lot of vocabulary words there. And also, you should be able to model constant velocity motion. Alright, so first we need to think about our system, and we need to worry about whether it can move, whether it can be squishy, whether it's flaily, that kind of thing, right? So if we look at our system, is it an object, right? Can we simply think of it as an object like we defined last lesson, right? Is our object rigid, which is very important. So can we assume our object doesn't have any internal parts, and that those parts, that our object doesn't move, one point in the object doesn't move relative to another position in the object? That's what it means to be rigid, right? Not squishy and not flaily. And those are words I kind of used for this, right? So if you look at this GIF here I have to the right, this is an example of a rigid object, right? So our object here, right, we can ignore the internal structure to an extent, at least for the time being. But looking at this, we see that it is actually our system here made up of different parts, right? We have a large sphere connected to a smaller sphere by some sort of bar of some sort. Right, but this is a rigid object because the locations of the points on the spheres and the bar don't move relative to each other. They can move all together, but it's not squishy. All right, that's what I'll kind of leave it at now. We'll definitely delve more into kind of stricter definitions of this later on this school year. Right? But if we can simplify our object, right, or simplify our system to an object, which we're going to be able to do in most cases, pretty much all cases for the time being, we're actually analyzing what's called the center of mass motion of the object. Right? Center of mass is just the average location of the object's mass. Right? It's going to be at one specific location in the object. So for example, if we had a solid sphere, right, the center of mass of that is going to be at the center of the sphere, assuming that mass is distributed evenly throughout the sphere. So maybe it's made out of, iron, but it's all the same iron throughout. It's not half iron, half cobalt. Now, the center of mass motion, so the motion of this point, is very predictive, right? We have equations that can predict the motion very well, right? So that's basically how we're approaching this. Oh, sorry about that. Okay, so let's talk about position, all right? So position, we're going to use the symbol X to represent it. So if we're writing an equation and it has the letter X, that's not bold, just regular font, that's going to represent position, right? Though it's not always going to be X. Sometimes we can use Y or Z or a combination of these depending on how many dimensions we're dealing with to represent position, right? So typically, if we're dealing with the horizontal position, we're going to use the symbol X, but if we're dealing with a vertical position, we usually use Y, though it really doesn't matter. You don't have to. But that's typically what's done for dealing with a two-dimensional system, which we'll be dealing with later on this unit. So position locates an object at a particular instant in time. Right? Now, the interesting thing about position is you need to say what your position is with reference to something, or else it doesn't mean anything. So for example, you might call your friend and ask where they are, and they're like, oh, I'm at the door. And they'll be like, at the door? What in the world are you talking about? Okay, well, what would be useful would be like, oh, I'm at the door at the front of your house. Well, now you know which door they're talking about because they refer to some other location, right? So what's going to be useful for us is to define a position with reference to an origin, right? Usually that's going to be where we call our zero position, right? It can be any arbitrary location. It doesn't matter, but some points are going to be more convenient to others, right? So usually we're going to set up a coordinate system, right? For right now, our coordinate systems will be one-dimensional. A little later this unit, they'll be two-dimensional. We basically will never have a three-dimensional coordinate system, but if we did, we could draw something like this on a piece of paper, which is how we try to draw 3 dimensions on 2 dimensions, right? 2 dimensions being your screen. All right, so that's position. That's pretty straightforward, probably not surprising. But we also have a quantity called displacement in physics, right? So notice here the symbol I have for displacement. We've got this Greek letter delta, which you might be familiar with from chemistry class, right? It's a symbol that's used to represent a change in a quantity, right? So whenever you see that delta, I do recommend you think in your head, all right, that's final minus initial of whatever it's in front of. So here, sorry about that, recording this at school. This delta is in front of the x, meaning that it's change in position, right? X represents position. Now, if you notice here, though, my x is not just a regular plain old x, it is bold font, right? So this is on purpose. This means that we're dealing with a vector quantity, right? So, oh boy, I'll talk about vectors in a second. But if you're looking at a textbook, typically any letter in an equation that's bold means it's a vector quantity. Now, writing bold is kind of difficult to do when you're taking notes, right? So what you should do is write whatever the symbol is and put a little arrow on top, usually pointing to the right. And I kind of try to type it up there. So you would write down an X with a little arrow up top, saying that it's a vector quantity. All right. So kind of moving on from my little blurbs there. So what is displacement? So displacement is the change in position of an object in a particular direction. All right. So displacement is representative of how far an object is from its initial starting point in a certain direction. Right? This is different from distance. Right? So distance traveled would be literally the length of the path that the object went, whereas displacement is literally kind of like the straight line path from start to finish in a certain direction. So there is a difference there. Now again, I'm throwing around this word vector. Let's talk about it. All right. So vector is a mathematical quantity, or construct, if you will, and it's a type of quantity that has both magnitude and direction. So magnitude means numerical value, right? So our value has some sort of number to it, and it also has a direction associated with it. That's why when I define displacement all over this page here, I kept referring to a certain direction. Right? That's because vector quantities have both magnitude and direction, so value and a direction. So here with the displacement, you would say something has a displacement of, let's say, 5 meters, but you have to include direction as well. So maybe they traveled 5 meters north. Right? Later on, we'll actually be using angles to represent the direction. Right? So vectors are super important in math and physics, right? Particularly higher level math, which is usually what's applied to physics, though welcome to algebra-based physics. But learn what a vector is. We're going to be referring to it throughout the course. It's very important. So just remember vector, all right, magnitude, and direction. All right, so that's what displacement is. So what's really wonderful about displacement is that the value of displacement is independent of the origin. So it doesn't matter where we put our zero in computing a problem. and our value of displacement is going to be the same no matter how we compute it, right? So you might be solving a problem, you put your 0 at one spot, and you find your displacement to be 6 meters to the right. Someone else solves a problem, puts their 0 somewhere else, and they end up with the same answer in the end. So that's what's really great, right? So what does this kind of mean applied to an example, right? So let's suppose you are standing 2 meters away from a tree, which is 2 meters away from a house. So I kind of diagram that here. So you, let's say we define you as the origin, right? So you're at position 0 meters. Your tree, if you look to your right, oh, there's the tree, right? So you have your tree 2 meters to the right, and then the house is 2 meters beyond that. All right, so that's what I have depicted here on the top. So I've kind of drawn a coordinate system here, right? I had said the right direction is my positive x direction. I'm 0, so the tree's position is 2 meters, and the house's position is at 4 meters. So if you travel to your house, right, and however long that takes, your displacement, your delta x, is going to be your final position minus your initial position. Well, if you end up at your house that has a position of 4 meters, and you started at 0, then 4 minus 0 gives us 4 meters in the end. So your displacement's 4 meters. So let's define our coordinate system differently. Let's suppose the tree is at our location of 0 meters. So you're still 2 meters away from the tree, right? But now you're to the left of the tree. That's the negative direction. So you're at a location of negative 2 meters, right? Whereas the house is to the right of the tree. That's the positive direction. So that's positive 2 meters now. So the value of our positions have changed. But if we compute displacement, our final position minus our initial position, we've got our house being 2 meters minus our initial location, which is now negative 2 meters. So 2 minus negative 2 gives us positive 4 meters. So our displacement is the same in both. Now, in neither of these did I say what the direction was. Sometimes it's easier to think about that after the fact, but the fact that our displacement value here is positive means that our displacement is rightward, since we defined our coordinate system to be positive in the rightward direction, right? So we'll kind of get used to this type of way of answering questions as we progress in class. So we also have a quantity called velocity. Velocity, we're going to use a bold symbol V, so it's a vector quantity, to symbolize it. Okay? So it's a measure of how fast it's going. In fact, velocity is the rate of change of position. If I didn't write that on the slide, I probably wrote it on the next one. So it's a rate of change, meaning it's with respect to time. It's some change in distance per unit time in a certain direction. All right? So velocity is a vector quantity. Now, when I deal with velocity, we're going to be dealing with something called average velocity as well as instantaneous velocity. So average velocity, I have a formula here actually to the right. It's going to be our displacement divided by the time it takes to go that displacement, right? So our change in position over a time. So this is going to give us an average value for the velocity. Sometimes the velocity will be constant, so our average value for velocity is going to be the value we're dealing with the entire time. Sometimes it's not. Our velocity value can change, so we actually are computing an average here. Instantaneous velocity would be if we were to take this equation and compute this value as time goes to 0, right? So we're doing a limit, if you will, if you're into math terms. So we're taking the limit as time goes to 0 for what our rate of change of position is. All right, so if we were to measure the speed in a certain direction at a split moment, that would give us our instantaneous velocity. We're going to be using instantaneous velocity a lot in equations, right? So you can kind of think of it, that's going to be the velocity at one precise moment in time. So when it comes to velocity, it is a quantity that's distance divided by time, so that's its dimensions. So distance is measured in meters and time in seconds, so its SI units are going to be meters per second. Right? So the last thing I want to mention before we move on to the next part of the next video is this equation here is, I said average velocity, technically it's average speed because this formula does not have direction embedded into it. So if you're computing average velocity, you do this computation, but then think about the direction after the fact. The direction of your velocity is going to be the same direction as your displacement, always and forever.